How are your friends gone?
I think I'm starting every day. But we still have him. He's pretty good. Because he goes hard. He'll go hard. We don't have Ethan, Matt, Brendan.
All right, we're going to start with some notes.
That's our start. They're all starters.
So the plan for today is cover half of the next section. Talk about some limits. Then we'll talk about day 10 homework. I'll collect that from you. Then we'll talk about day 11. The day 11 was quite a bit trickier, so I'm going to give you that to take home and clean up over the weekend. So on Tuesday, I will collect day 11 and then this day 13 homework, which you'll do after we cover the lesson. Okay. Tests are graded. I'll have the scores online, hopefully next period in case something comes up. If not next period, then usually by the end of the day. You can see how you did. Day 12 was the test. We count every day, except Saturdays and Sundays, and days off, and summer days. Okay, here we go. We're going to extend the concept of of limits into continuity. So there are two components to continuity. One is the logical part of it, which is a very easy explanation, which you can all get in about 2 seconds. The other one is the mathematical aspects of it, which is a little bit more complicated, but still not that tricky. Okay. We've got some continuity. We've got some one-sided limits. We've got some properties of continuity, and then we're saving this for Tuesday, the intermediate value theorem. There's a rule in this class: if a theorem has its own name, it's important. Okay. But again, that's for Tuesday. Okay, here we go. So let's start with a simple question. What does it mean for a function to be continuous? Go.
It goes on for an infinite period, or like a specific period.
Let's talk about continuity on a closed interval. So from A to B, in the interval from A to B, what does it mean for a function to be continuous? Well,
Unbroken over that period?
unbroken over that period. How's that sound? Makes sense? How, if I give you a picture then, could you tell me if the function is continuous or the opposite of that is discontinuous?
I think so.
What would make a function discontinuous?
Like poles,
Good. That's one of the three.
asymptotes.
That's two. Done. Third one.
The sets of equations where it's like if it's greater than x, we'll do that.
What are those called?
I don't remember.
Piecewise functions.
Piecewise.
You got all three.
All right.
Why am I here? Here. No. Excuse me. Question? Comment?
Never mind.
Now we're good? Okay. So here's the easy part, is the stuff in blue. The question you want to ask yourself, looking at a function, is can I draw this function without picking up my pencil? If the answer is yes, then the function is continuous. If the answer is no, then it's discontinuous at certain points. And it would be nice if we just had to deal with that, but of course there's a mathematical aspect to it that we want to talk about. No, not that difficult. This is actually pretty straightforward. It's not going to be that would be gross. All right, so here's the fancy mathematics stuff. So a lot of times what I'll do is I'll give you things written in English, but I'll also give you the what I call calculus speak, because you need to understand what this means also. Okay, so we're starting with the function f. It's continuous at c, so at some particular point, and we're actually going to look at all of a bunch of that's horrible English, at a whole bunch of different c's. And if it's continuous, three things have to be met. Number one, it has to be defined. F of c is defined. There's a value of the function. Number two, it has to have a limit at that point. Number three, the answer from part one has to equal the answer from part two. And then there's a bunch of other stuff down here about open intervals and things like that, but these three are the big part. So then what I want to do is look at the three things that cause problems. and then talk about why they aren't continuous based on this definition. Okay, this is what's considered the definition of continuity. So when you're asked, why is a function discontinuous, you can't say, because I tried to trace it with my pencil and I couldn't do it. That's not a mathematically valid explanation. What is a mathematically valid explanation is because it violates one of these things, and I'll show you what that means in a second. Okay, we good?
So you need all three of them?
Correct. And I'll show you, again, we'll look at one that doesn't work and you'll see what I mean by having all three. Good? All right. Here's the first one. Technical term is a removable discontinuity. You know it as a whole. And we talked about these already. You get a whole from part of a function canceling. And so let's look at that point x equals 1 and go through the three definitions. Is the function defined at x equals 1? No, there's no value there. So we're done, it's discontinuous. But we'll go through the rest of them. Does it have a limit at x equals 1? Yeah, what is that limit, by the way? 2, good. And then part 3, does your answer from part 1 match your answer from part 2? The answer is no, because 1 doesn't work. Okay, so removable discontinuity, also known as a whole, that's the first type. The second type is a jump discontinuity, which we've seen already in piecewise functions. I'm sorry? LH. Yeah, it's coming. Yeah. Okay, so is that function defined for all values of C? Yes. Even though there's a hole there, that hole's filled in by that one up on top. So it satisfies number 1 of the definition. It is defined at all the values of C. Does it have a limit at all points? No. Where doesn't it have a limit? -2. Why, Colin?
Well, the left-hand side is the same to the right, since there's no right.
Perfect. Left-hand limit doesn't match right-hand limit. No limit. Therefore, 1 and 2 don't match. Discontinuous. So as soon as you violate one of those 3, it's no longer discontinuous and we have a problem. And then the third type is an infinite discontinuity, which you know is an asymptote. This one is a train wreck. It's not defined, it doesn't have a limit, and therefore those 2 don't match. However, be aware of, if I come out here to x equals 2, let's talk about that for instance. Is the function continuous at 2? Yes? Is it defined at 2?
Yeah.
Does it have a limit at 2? Is the value of the function the same as the value of the limit? Yes. Good. So it would be continuous at 2. The problem comes in over here. Okay. So now we talk about where is it continuous, where is it discontinuous. And you will see the question asked both ways. Where is this function continuous? Where is this function discontinuous? Usually the discontinuous is easier to answer. All right, let me give you another scenario. Oh, that point's supposed to be above the big, here, we'll just fix it that way. There you go. And we'll put this at 7. So the obvious question is, looking at that, can I draw that without picking up my pen? The answer is no. So we know the answer is going to be discontinuous. Why? Question.
No, I have the answer.
I haven't
Can
asked a
the
question.
first? Okay, you have.
What question do you think I'm going to ask?
How do we know that it's not continuous?
How do we know it's not continuous?
Because the limit as x approaches c is not equal to f of c.
Beautiful. What's the value at 7? Oh, I guess I need some points here. Let's make that 3 and we'll make that 4. What's f of 7? 4. What's the limit at 7? 3. Therefore, we violate the third rule, which 1 and 2 don't match. So this is one of the instances where the third one gets violated. Most of the other ones were all 1 and 2. So a hole with a point above or below it will cause the third part to fall apart. Oops. There we go. Okay, let's look at that function. What does that function look like?
Half circle.
Sorry?
Half circle.
Half circle, which one? Is that you, Nick?
Yeah.
Top, bottom, left, or right?
Top.
Top. What's the radius?
2.
Good. So either sketching in your notes or picturing it in your mind, what's the limit as x approaches -2 of that semicircle? Again, we have the top half of a circle going from 2 to -2 because he told us the radius is 2. What's the limit as you approach -2 from the right?
0.
0 is correct. What's the limit as you approach -2 from the left?
Doesn't exist.
Why?
Because the function isn't defined on the left side.
Hold on. Good.
Yeah, so you can't square negative.
So specifically in this problem, you can't take the square root of a negative answer. In general, dead on. The function's not defined out there. You have nothing to talk about the limit. For those of you that are visual learners, it looks like this. Coming from this direction, we're fine. We're getting closer and closer and closer to eventually reaching 0. That's great. If I go this direction, I'm okay with 0 too. But now, if I move to the left-hand side, I have nothing to work with there. The function is not defined. Therefore, it can't have a limit. In order to have a limit, the function has to be defined. This is what's called a one-sided limit. It doesn't happen very often because most of the functions that we deal with continue off into infinity on the left and the right. But occasionally things like semicircles and even some of the piecewise functions will cause some issues there. Okay. And then remember we talked about the 3 parts of that. -2 coming from the right, -2 coming from the left, and at -2. So this case, for instance, just as a quick review, the limit as x approaches -2 from the right of f of x is 0. The limit as x approaches -2 from the left of f of x does not exist, and therefore the limit at x equals -2 of f of x does not exist. And these two have to match in order for that to work. And we know that already. Okay, so let's talk about this. You know that already, but you should still be exposed to and understand the notation that's going on in that box there. So we start with a function f. It could be any function, and we start with a point C somewhere on the function. What does L represent? Value of the limit. The limit of f of x as x approaches C is L if and only if. Do you remember if and only if from geometry when you did a logic unit? What does it mean?
Only if
Oh,
is
thanks.
that
Great.
only in one circumstance.
No, it actually means both ways. So it's a reversible statement. So for instance, if I make a statement like, if an animal is a dog, then it's a golden retriever, can that be written as an if and only if statement? No, because not all dogs are golden retrievers. All golden retrievers are dogs, but not all dogs are golden retrievers. Okay, so it's got to work for both directions. I'm trying to think of an example. Give me a second. If I'm married, then I have a spouse. If I have a spouse, then I'm married, so it works both directions. The same is true here. In order for it to have a limit, it has to work coming from the left and coming from the right. So that's the fancy way of saying the left-hand limit has to equal the right-hand limit. One of the difficult things that you're going to run into is figuring out when do I need to know the calculus speak in the box, and when can I just say left-hand limit equals right-hand limit. In this instance, the left-hand limit equaling right-hand limit is good to go. Everybody universally knows that. But if you need to justify why something is not continuous, you can't just say because I couldn't draw it without picking up my pencil. Right, so that's something that's going to cause some problems as we go on. How detailed of a definition or a theorem do I have to know? We talked about that already from left and right. We're good to go. Properties of continuity. You can write this down, but it's real simple. No matter what you do to a continuous function, it's going to stay continuous. No matter what you do with two continuous functions, it's going to stay continuous. You multiply a continuous function by a number. You add two continuous functions. You multiply continuous functions. You divide continuous functions. It'll stay continuous. Notice there's a little caveat there, except where the denominator equals 0. There's a third part, or another part, a fifth part I should say, that comes up later, and it also applies to composite functions. You take a continuous function, you put it into another continuous function, the result is continuous. So you pretty much can't screw it up. If you're given a complicated function, you can determine if it's continuous by looking at the individual parts. You know, so you want to figure out if x plus 1 times the quantity x plus 2 is a continuous function. Instead of looking at the quadratic, look at the individual parts. If x plus 1 and x minus 2, or whatever I said, are continuous, then the product will also be continuous. Really important. Polynomials are always continuous. You're going to use that a lot to justify some of the theorems we're going to get to in the future. It must be important because it's in red and it's very large. The catch is you need to know what a polynomial is. Do you all know what a polynomial is? No? Okay. What isn't a polynomial? Four. 4 is actually a polynomial
Trig,
because that's 4x to the 0 power.
trig function.
Trig functions are not polynomials. What else?
Absolute value function.
Absolute value is not a polynomial.
That
You're like a wellspring of information today, Danny. What'd you say, step function?
that function.
Step function, another one, not a polynomial. How about x squared plus 1 over x?
Yeah. Not a
No, it's a rational function. So denominator or a fractional functions will not be polynomials. Talked about that already. Composite function. Let's talk about the tangent function. Where is it continuous? And I can ask this question one of two ways. I asked it, where is it continuous? I could also ask, where is it discontinuous? So what causes problems for the tangent graph? Asymptotes. And where do those asymptotes happen for the tangent graph? No.
over 2.
I over 2, correct.
That's funny.
So where is it continuous? It's continuous everywhere except the asymptotes. How many of them are there? Infinite. Pi over 2 plus. No. Pi k as a period of pi. So this is where the function is discontinuous, but I want where it's continuous. So how do I take this and express all the rest of the graph? Yep. Okay, so what is that saying? That's saying go from negative pi over 2 to pi over 2. Don't include them, and then repeat that process ad nauseum.
That would be pretty nauseating.
I'm sorry?
That would be pretty nauseating.
Yeah, ad nauseum. Do you know what that means?
Just to the point of boring.
It's actually Latin that translates as until you puke.
That's awesome.
Hmm?
That's awesome.
Well, feel free to use it. Now the weird thing is, question.
Is it only, like, is it not 2 pi because
because the period for tangent is pi. If it were a cosine or a sine graph or something, you know, cosine, sine, secant, or cosecant, it would be 2 pi k. But for tangent and cotangent, the period's only pi. Yeah, so there's the picture. We want all the black part of the graph. We want to eliminate all the asymptotes. Okay, we're going to stop there because, yeah, good. We don't want to start the intermediate value theorem yet. We'll save that for Tuesday. I don't think there's any homework tonight that involves, then just skip it, and we'll pick up where we left off on Monday. So let's start with day 10, because I think those problems were a little bit easier, and then we'll transition on to day 11, where they got a little bit nasty.